Let's look at a few of the patterns for drawing resonance structures. And the first pattern we're going to look at is a lone pair of electrons next to a pi bond. And so here's a lone pair of electrons. I'm going to highlight it in magenta. That lone pair of electrons is located on this carbon. Let me go ahead and put this carbon in green here. And I'm saying there's a -1 formal charge in that carbon in green. So that carbon in green is also bonded to a hydrogen. So once again, you need to be very familiar with assigning formal charges. So we have a lone pair of electrons next to a pi bond, because over here we have a double bond between the carbon and the oxygen. One of those bonds is a sigma bond, and one of those bonds is a pi bond. So I'm just going to say that these are the pi electrons. So our goal when drawing a resonance structure is to delocalize that -1 formal charge, so spread out some electron density. And so we could take the electrons in magenta and move them into here to form a double bond between the carbon in green and this carbon right here. And that'd be too many bonds to the carbon in yellow. So the electrons in blue have to come off onto this top oxygen here. So we go ahead and draw in our brackets, and we put our double-headed resonance arrow, and we draw the other resonance structure. So we have our ring, like that, and then we have now a double bond between those two carbons, and then this top oxygen here now has only one bond to it. The oxygen used to have 2 lone pairs of electrons. Now it has 3 because it just picked up a pair of electrons from that pi bond. So let's go ahead and follow the electrons. The electrons in magenta moved in here to form our pi bond, like that. And the electrons in the pi bond in blue moved off onto this oxygen. So I'm saying that they are those electrons. That gives the top oxygen a -1 formal charge. And so we have our 2 resonance structures for the enolate anion. We know that both resonance structures contribute to the overall hybrid. And if you think about which one contributes more, for the example on the left, we had a -1 formal charge on the carbon in green. So that's a carb anion. And for the resonance structure on the right, we had a -1 formal charge on the oxygen. So that's an oxyanion. Oxygen is more electronegative than carbon, which means it's more likely to support a -1 formal charge. And so the resonance structure on the right contributes more to the overall hybrid for an enolate anion. All right, let's do another pattern, a lone pair of electrons next to a positive charge this time. So let's look at nitromethane, and we could look at this lone pair of electrons here on this oxygen, and that lone pair of electrons is next to a positive charge. This nitrogen actually has a +1 formal charge on it. And so let's think about drawing the resonance structure. So our goal is to delocalize charge, to spread charge out. We could take the electrons in magenta and move them into here to form a double bond between the nitrogen and the oxygen. But that's too many bonds to this nitrogen. That would give us 5 bonds to that nitrogen, which we know doesn't happen because of nitrogen's position on the periodic table. So that means that the electrons in this pi bond here are going to come off onto the oxygen. So these electrons in blue come off onto this oxygen. We draw our other resonance structure for nitromethane. So we have a CH3. We now have a double bond between the nitrogen and this oxygen. This oxygen used to have 3 lone pairs of electrons, but the electrons in magenta moved in here to form this bond. And so that means we have only 2 lone pairs left on this oxygen. For the oxygen on the bottom right, there's only 1 bond now between the nitrogen and the oxygen because the electrons in blue moved off onto this oxygen. And that means this oxygen has 2 more lone pairs of electrons. And so when we go ahead and put in our resonance bracket here, you always need to think about assigning formal charge. So what happened to the charge? Well, this oxygen now has a -1 formal charge, and this nitrogen still has a +1 formal charge. So we've delocalized that negative charge. It's actually over both of those oxygens. And notice that the overall charge for nitromethane is 0 for both resonance structures. So we have 1 positive charge and 1 negative charge on the left, so that gives us 0. And we have 1 positive charge and 1 negative charge on the right, so that gives us 0. So conservation of charge. All right, let's do another example for a pattern that we might see. All right, so for this one, we have a positive charge next to a pi bond. So let's look at this carbon. So I'm saying it has a +1 formal charge. And if it has a +1 formal charge, it must have only 3 bonds. And since it's already bonded to another carbon, so it's already bonded to, let me go ahead and label these. So the carbon in yellow there is bonded to this carbon in green. Because it has a +1 formal charge, it must have only 2 other bonds. And so those must be to hydrogens. So I draw on those hydrogens. And so now it makes a little bit more sense why it's a +1 formal charge. It'd be 4 minus 3, giving us +1. The carbon in green has a formal charge of 0, so it already has 3 bonds, so it needs 1 more to hydrogen. And let's go ahead and let's make this carbon over here let's make it red. So this carbon over here in red already has 2 bonds. It has a formal charge of 0, so it needs 2 more hydrogens. So once again, our pattern is a positive charge next to a pi bond. So let me go ahead and highlight these things here. So we have a positive charge, right, next to a pi bond. And so here, let's say this one is our pi bond, like that. So when you're drawing resonance structures, again, your goal is to delocalize that charge. And so we could spread out that positive charge by taking the electrons in blue, the pi electrons, and moving them into here. So let's draw the resonance structure. So we now have, we would now have a double bond between the 2 carbons on the right. The hydrogens haven't moved, right? So I'm going to leave those hydrogens in there. So there's still 1 hydrogen on the carbon in the middle, 2 hydrogens in the carbon on the right, and 2 hydrogens on the carbon on the left. So the electrons in blue moved to here, like that. So let me go ahead and highlight those carbons. So the carbon in green right here, and the carbon in red. So what happened to the +1 formal charge? Well, you can see that it's actually moved to the carbon in the red. The carbon in red right here has only 3 bonds. So 4 minus 3 gives us a +1 formal charge. And let's go ahead and finish our resonance bracket here. So I put that in. And so when you're doing this for cations, you're not going to move a positive charge. Right? So when you're drawing your arrows, you're showing the movement of electrons. So the arrow that I drew over here, let me go ahead and mark it in magenta. So this arrow in magenta is showing the movement of those electrons in blue. And when those electrons in blue move, right, that creates a +1 formal charge on this carbon. And so don't try to move positive charges. And remember, you're always pushing electrons around. And then finally, let's do one more. All right, so for this situation, we have this is for acetone, right? So we have a carbon right here, double bonded to an oxygen, and we know that there are differences in electronegativity between carbon and oxygen. Oxygen is more electronegative. So what would happen if we took those pi electrons? So let me go ahead and highlight those. I've been using blue for pi electrons. So these pi electrons right here. And we move those pi electrons off onto the more electronegative atom like that. So let's go ahead and draw our resonance structure. All right, so we would now have this top oxygen would have 3 lone pairs of electrons. One of those lone pairs are the ones in blue, those pi electrons. That's going to give the oxygen a -1 formal charge. And we took a bond away from this carbon. So we took a bond away from this carbon, and that's going to give that carbon a +1 formal charge. And so when you think about your resonance structures, first of all, I should point out that 1 negative charge and 1 positive charge give you an overall charge of 0. So charge is conserved, and over here, of course, the charge is 0. So you're thinking about the resonance hybrid, right? So we know that both structures contribute to the overall hybrid, but the one on the right isn't going to contribute as much. So this one on the right is pretty minor. And that's because you have a positive and a negative charge. And the goal, of course, is to get to overall neutral. But what's nice about drawing this resonance structure and thinking about this resonance structure is it's emphasizing the difference in electronegativity, right? So for this one, you could just say oxygen gets a partial negative and this carbon right here gets a partial positive. So that's one way of thinking about it, which is very helpful for reactions. But drawing this resonance structure is just another way of thinking about emphasizing the fact that when you're thinking about the hybrid, right, you're thinking about a little bit more electron density on that oxygen. All right, so once again, do lots of practice. The more you do, the better you get at drawing resonance structures. And the more the patterns, the easier the patterns become.